Hello children, welcome to Yamuna's physics classes. We have to discuss Faraday's laws of electromagnetic induction. Chapter 6 and the topic 6.4. Before coming to the laws, we need just a recap of the experiments done by Faraday and Hertz. They together did few experiments before they came to the law. So the experiment is simple. The experiment is like this. They had a coil of wire. You can see 3 coils are here, and these 3 coils were connected to a galvanometer, and a magnet was brought close to the coil, then taken back. So the experiment was initially like this. First step, the magnet, the north pole of which well moved into the coil. At the time there is a deflection in the galvanometer. Keep it steady. The magnet was kept steady or stationary inside the coil. No deflection. Then again it was brought back. The north pole was taken back. At the time also the deflection was there, but in the reverse manner. So it's very clear the direction of the EMF. So at the time you see there is deflection, that is known as induced EMF. Induced in the sense you are not bringing them into contact, that is conduction. Induction means neighboring, need not have a contact in between them, then you say the word induction. So direction of the EMF depends on the direction of motion of the magnet. If it is pulled in, then you can see, if it is pushed in, you can see it is towards right. If it is pulled out, you can see the deflections towards the left. So that was one experiment. And the second experiment was, instead of moving this magnet, you can do with the coil itself. The coil can be, keep this magnet stationary. First bring the coil towards the magnet. Then you will see a deflection. Then take the coil out or back. Then you will get the deflection in the reverse manner. So that was the second experiment. And the third one was, instead of the magnet itself, the magnet is taken, and instead of that you place a current carrying coil with a switch. You know, current carrying coil can produce magnetic field. Same concept we have done in lesson 4. A current carrying coil can produce magnetic field around it. So we place, instead of a magnet, what's the purpose of magnet? You need magnetic flux or magnetic lines of force. The same is okay when you are taking the magnet, removing the magnet, and instead of that you place a current carrying coil, another coil similar to this with current. So you have a cell for that to pass the current, and you have a key or tap key is there. Whenever you switch on the key, at the time there is change in magnetic flux, so there is an induced EMF. When the tap key is taken away, you can see that again there is current. But keep on pressing the tap key, you won't see any deflection. So all the 3 experiments done by Faraday and Hertz finally led to the conclusion known as first law and second law of Faraday. So first law specifies the reason. First law gives the reason of induced EMF. I told the word induced EMF. Why induced? Induced means something is happening in neighboring or the neighborhood, and then it causes current. That is why the term induced, and EMF just because there is voltage fluctuation. So first one was the reason. Whenever the amount of magnetic flux linked with the circuit changes, only when there is change, once you keep the magnet stationary, no deflection. Only when you are pushing and pulling, only then you have EMF. So what's the reason? Simply the reason is the change of flux. Whenever the magnetic flux linked with this circuit is changing, only then you will have induced EMF. So that was the reason. That's the first law. And second law, same as Newton's second law, measures force. First law would explain the term force. So second law is giving F equal to ma. Similarly, the second law says the magnitude, underline the word magnitude. Magnitude of the induced EMF in a circuit is directly proportional to the rate of change of magnetic flux. If you move slowly, Accordingly, the deflection will be slow. If you move fast, the deflection will be fast, showing the rate. Rate means the time you are using to put in or pull out. That time you are taken is a matter of fact. So if it is fast, then you have more flux. If it is slow, you have less flux. Meaning, the rate of change of magnetic flux is proportional to induced EMF. So, proportionality constant here is 1. Maybe you will think why there is no proportionality constant. For sure, it is 1. And with a minus sign. This minus sign specifically gives the direction. What is the direction of the current? I told you either it is towards right or towards left, depending on the motion. So that direction of the induced EMF is given by this negative sign known as Lenz's law. That is discussed in another topic, not this. So that is why you have a minus sign here. Very, very important. This minus sign shows the direction of the induced EMF. And second law gives only magnitude of the induced EMF. Now, once you know the EMF, next step it is current. What is current? Ohm's law. V is equal to I into R. So what is I? V by R. Here E is the voltage, R is the resistance. So taking the ratio, you will have minus 1 by R into d phi by dt. So from here you can see that resistance is also a factor for current. But here resistance is not a factor. Just think about the rate of change of flux. For example, if you have resistance for two different coils, suppose you have copper wire and at the same time silver wire. If you do the same experiment with copper wire and silver wire, the current will be different. Why? Because copper has more resistance compared to silver. So if you are using copper wire, the current will be less. If you are using a silver wire, the same thing, current will be more. No change in number of turns, then the time through which you are doing, all these remaining the same. The other factor remaining the same. If you are using copper and silver, the current will be different because induced current depends on resistance also. Now, if you come to charge, third lesson, current electricity, you know, I is equal to dq by dt. Rate of flow of charge is known as current. So I can write instead of I dq by dt. Here the time is the same, cancels. So you can see dq or the charge produced is independent of time. No dependency of time. So whether the rate of flow means what? Either slow or fast, is independent on the charge produced. So the charge produced during this movement is independent of time. Whether it is slow, whether it is fast, the same number of charges is going to be developed. So two important factors. Here you can see R is independent, here R dependent, here again R dependent, but here again independent of time. So all these keywords you need when you go through a problem. So what is Lenz's law? You will go to the next video, but here you have only magnitude. So for the summary, what is Faraday's law? Number 1, the reason. What's the reason? Whenever there is change in magnetic flux, only then you have EMF. Second thing, what is the value? The magnitude is simply proportional to rate of change of flux. Higher the rate of change, higher the EMF produced. Okay, so you can have a screenshot. Thank you for listening.